And this is our last presentation for this sessions, and is from Emad Al-Momani from Intel, and his presentation is on a new desktop socketing approach to boost operating frequencies. Emad joined Intel in 2011 as a mechanical engineer, responsible for the design and development of validation socket interconnect solutions and technologies for the Intel products across all market segments. Emad, please go ahead.
Sure, thanks, Ying. As the title here suggests, basically, like we're trying just here to, like it's an experiment to try to replace existing desktop socket pins with mainly shorter bins. That's kind of a very high level summary. So we did look to other socket technologies that is mainly shorter. And I will explain why we are interested in the shorter bins. And this is kind of mainly the whole presentation topic here is summarizing this work. The agenda for this presentation, I will start with the problem statement, then we'll describe the second level interconnect, that basically the socket is a very core part of it. Then we'll go to the current desktop LGA socket, and also just to show how it looks like, and for those who may be not familiar with it, and also explain the other two socket technologies that have been studied during this experiment here. We'll go over some of the board modifications that we had to do in order to enable socketing with the new socket technologies. Then we'll provide a summary for the performance, comparing basically the baseline socket, the LGA socket versus the other two sockets. So that's kind of mainly the overall agenda. As of a problem statement, the problem statement or the purpose why we are doing this work. If you guys look to the right, to the image here, this is an LGA desktop socket. As you know, this desktop packages are LGA packages, and it will need an LGA socket for sure. This socket, as can be shown here, is a cantilever type socket, and we'll see an image for the bin in a second. And the height for this bin is about 3 millimeters. With the current, or like with the ongoing more demand for higher frequency, higher DDR data rates, I mean, we have some concerns about this long bin mainly. The overall degradation budget available for the end-to-end signal channel is getting kind of smaller and smaller. And for sure, this kind of long bin is contributing or consuming a good portion of it. So the work here is a trial to see basically can we improve by introducing other socket technologies. So we are just trying to see the performance of these technologies that I will show in a second. So that's kind of the motivation and the driver behind this experiment. This is a very high kind of level diagram of the second level interconnect. You can see in the middle side here, we have the socket, and the yellow is a representation of the socket pin. This kind of socket is a little bit high, kind of long, as I mentioned, and there are some advantages for that. As you can see, there is the decoupling capacitors placed within the socket bin field, and also there is the package land side components here that is also can be cleared by using this high socket. These are some of the challenges that we will face when we move to the other technologies that I will go over. And again, the signal path, very high level, will go from the silicon through the package traces and vias, all the way through the socket bin here to the motherboard, and will keep going to the DDR, or basically the DIMM card and the memory packages here through the DIMM connector. So this kind of path is mainly very, very critical, especially with at higher frequencies. So every single piece of this path need to be very well studied and optimized. And for sure, as you can see, the socket is consuming about 50% of the Z height stack of this basically path that we're seeing here. On the left side is an image for the LGA socket. Again, you can see the bin field decoupling capacitors placed here. Bottom side, we can see a cross-section of the LGA socket bin. It's a cantilever bin, as you can see here, soldered down. This socket will be soldered down to the motherboard. Height is about 3.2 millimeter almost. And one major thing to notice is the offset that you are seeing between the socket, basically, or the package pad and the PCB pad. So this cantilever design force this offset to happen, like in order I mean, we need this offset to be there. And going to the right image here is an image for an elastomer socket, one of the technologies that we're going to be talking about today. This technology is very short relative to the LGA socket. Uncompressed at 1 millimeter pitch, which is the pitch for this package, is about 1 millimeter. Compressed will go close to 0.8 millimeter. So this will leave us with about 1/3 the height of the POR bin that we currently using. Okay. So digging a little bit further on what are the socket technologies that we are considering in this study, elastomer is the first one, both basically, and the second one mainly is what we call SOGO bin. It is a single piece stamped and rolled metal bin. And the reason why we moving or going to this kind of bin is because it is an economic option. The cost is one of the major concern when it comes to OEM sockets. So elastomer, I will, before going there, like both bins are a dual compression type bins that you need to apply force from both sides and to apply to engage those bins and get the right stroke to achieve the electrical connectivity. Both of them are non-soldered to the platform, so there is no need to solder those bins to the platform for sure. The elastomer is, for those who may be not familiar with it, is mainly a metal powder that is suspended within an, I would say, silicone rubber body. When you apply the force on this kind of elastomer bin, these little metal particles will get in touch with each other and mainly will form an electrical path between the package and the PCB. So these are the two technologies that we are considering here. Again, the elastomer is about close to 0.8 millimeter compressed. This SOGO bin is about compressed is about 1.2 millimeter. So both of them are shorter than the almost like 30% to I would say 45% of the original or the current desktop socket bin. Okay. I would like to highlight a few of the things that we had to do to the platform to enable the new socketing options. As I mentioned, these both technologies are shorter in height, and which is the driver or our target is to use these short bins. Again, if you look to the motherboard here with all these cabs, decoupling cabs here, mainly there's no way we can support the new sockets while these are here. If you look at it, this is an elastomer socket, just a schematic, placing it with the current platform design. There is these cabs here about close to 1.8 millimeter in height. You have some land side component on the package itself about I would say maybe around 0.5 to 1 millimeter in height as well. And if you try just to socket this package to the platform, these will collide. So what we had to do to enable the socketing, we re-spinned the whole platform designed a new platform where we introduced a cut in the center of the package that you can see here. With that, mainly, like we had to move all these kind of cabs to the secondary side of the board. Any previously existing components at the bottom side or the back side of the PCB were also moved around. The one major thing that we have tried to keep here not touched is the DDR channels on the platform. So there been some changes to the platform that could affect, could have impacted a few other things like maybe power stuff. But again, from DDR DDR, which is the main target, we did make sure that these channels are stayed the same. So we can have a one-to-one comparison later between the original platform and the new platform. Okay.
Emad, before you
So,
move on, there's a question that
sure.
the question is the trace length on the motherboard much longer than the 3mm socket pin length? I think that's probably your previous slide. And would it be
Yes.
easier to shorten the PCB trace instead?
That's right. No, I think the trace length will depend on where the DIMM card are located versus the CPU mainly. So I expect it to be longer than the bin height of 3mm. Yeah, I mean, there is always a strive to move those cards closer and closer to the CPU, but that also faces some other challenges from mechanical and other aspects. So I think, yeah, I hope this answered the question.
Okay, thank you.
Just a picture for the current system on the left side here. You can see our current or the original platform. We are using the OEM heatsink on this platform here. As you can see it, on the right side is the new platform with the introduced center cut into the package area. The plating here is an OSB plating, which is not ideal, I will say, for this type of application for the elastomer and for the other SOGO bin socket. We did not, kind of for other reasons, like we were not able to change the plating on this platform this time. So we kept the OSB, but again, what we did, we mainly tinned the pads, added some thin layer, solder layer to those pads just to get rid of the OSB finish here, and hopefully providing better connectivity between the elastomer socket and the SOGO bin socket with the motherboard. On the mechanical side, the thermal side, we used a different heatsink than the OEM one. I have an image for it here on the bottom side. The driver behind moving to a different heatsink mainly is the force needed for those socket technologies, the new socket technologies. Elastomer requires about 25 grams per pin. That SOGO bin is much lower. I believe it's about 12 grams per pin. But again, the higher force needed with the elastomer forced us to go with a larger, basically like a more stronger heatsink. So that's from the heatsink perspective. So the kind of the disqualification here being through two major folds. The first one is functional testing. Mainly, we looked at quantifying the added advantage of the new socket technologies relative to the current baseline, the cantilever type bin. And the second actually portion was mainly on the reliability side. So we are aware of some major concerns about the reliability of these kind of new technologies and its ability mainly to stay functional for the product, like in the product environment for the whole product life cycle. For that one, actually, I details here will not be covered in this presentation, but I can say very high level that we have some very initial good results running some stability testing, long-term stability testing, thermal cycling, baking, some high temperature, high humidity, stuff like that. So overall, we have some, I think, initial data that could be promising for this type of solutions, and hopefully maybe in future events we can talk more about it. Going to the results here. What I'm showing here is mainly the baseline results, and for what you can mainly see here, like we have used what we call rank margining tool, RMT. It's a software tool that will exercise the DDR bus. So mainly this tool will write to the memories and it will read back from those memories. And while doing that, we collect the margins in both kind of picoseconds and millivolt. I will show in the next slide the eye diagram. Mainly these are the x-axis on the eye diagram, and this is the y-axis on the eye diagram. And generally, we want these values to be as large as possible. The larger these values, mainly the larger the area on the eye diagram, and the more margin you have in your solution. For this specific platform and channel, guidelines that we need things to be more than 120 picoseconds and millivolt to be in the low risk region. When this values start to drop, we get to the mid risk at about kind of 100 picoseconds. Once you drop below 100 picoseconds and millivolt, you are in the high risk region. And high risk here means basically that you may start to see some functional issues when you're running the system at full speed. We have overclocked this platform to about 3,500 megatransfer per second. The POR speed on this platform was about 2133 megatransfer per second. So almost the double of the original speed, about 80% higher. So that's kind of the initial results that we got here for the original socket, the LGA socket. As you guys can see, we are in the high risk region. For example, for this one here, the read, we are in the high risk. At the right, also in the timing, we are in the medium to high risk region as well. When it comes to the millivolt voltage, things a little bit is better here. Again, still seeing things dropping to the high risk region. So mainly running the original platform with the original socket at this speed is not a good thing to, or like it has. We should expect some issues doing that. Moving to the next slide, mainly looking at the performance of the new socket technologies, the elastomer and the SOGO bin. You can see here that these sockets are getting higher values. They are mainly moving to the low risk region. Overall, I would say the standard deviation or the scatter of these data is acceptable. In general, like we're seeing some, like for some reason we are seeing one or a few points that's getting much lower here on the elastomer side. I don't know what's the exact reason caused that, but overall things are in the much better shape than what we have seen on the LGA socket, which is the baseline shown here. That applies to mainly the right read as well is in very good shape. Elastomer, of course, showed much better performance, or like higher or better performance than the SOGO bin. I can see this is getting to a little bit lower than what we would like to see in this case here. On the I would say on the voltage side, things are much better. I would say all of them falling on the green area or above this green line means a low risk area. So this is very good indication telling us here that, okay, these new socket technologies are giving us some advantage. We are kind of, if you look here, like the original socket is about 100 millivolt. We are getting about more than 200 millivolts with the elastomer, for example, here. You're talking about 2 folds of the millivolts. Generally speaking, we consider about every 20, or at that time, over 20 millivolts to be one speed bin in our package binning. So there is some advantage for sure in going shorter in those bins. So I think this is kind of mainly the results of this experiment. In summary and conclusion here, I believe we have some, with these kind of dual compression sockets, the elastomer and the SOGO bins, they are showing us very or promising speed advantage over the original socket. Of course, these are driving some change to the platform to accommodate the mechanical side, and this will drive some new approaches when it comes to power delivery and power integrity. The material of elastomer, if it ends up to be chosen as an option, is still also, we have some concerns about it, especially in the harsh environment where like the overclocking, customers may need to expose these platforms to N2 or dry ice or do some oil submersion. So long-term quality and reliability is a concern, and it needs further attention basically and study. The cost of these elastic kind of options is also maybe not as low as what we are enjoying with the current socket, OEM socket. So more work on the cost side is needed. Kind of getting the suppliers ecosystem to meet the HVM requirements is another challenge. And of course, like getting OEMs to adapt to these and also end users to accept it is also another kind of thing to work on. So that's mainly what I have here. So please let me know if you guys have any questions.
Thank you, Emad, for the presentation. There are a couple questions came in. The first one is, I think, back to when you were talking about the elastomer socket. The question was the cantilever method gives a swiping action when compressed that might help clean the contacting area. Is the non-swiping action of the elastomer alternative an issue?
Yes, actually, that's a very good question. Yeah, we at least so far, like we've been using these elastomer in the validation environment for years. It's been working for us very well, no problem. I believe as long as the contact on the package side is a noble contact and be enigmatic plating, I think this shouldn't be a big concern.
Okay. The next question is, can you share the SOGO pin diameter and the device pitch?
Yes, the pitch size, the device is at 1 millimeter. Actually, the diameter, I don't have it on top of my head. I think in the range of 0.3 to 0.4 millimeter, in that range.
All right. The next question I have is for the LGA data that was the data from the same board they used for the other two, or if it is not, then what variation is the PCB layout differences?
Yes, actually, yeah, it is not exactly the same board. Mainly, we had to respin the design and manufacture a new board. Let me go to that image here. It's a different one where we introduced this cut here. Yeah, so it is not, I would say, 100% apple-to-apple comparison, but as I mentioned, we have kept all the DDR basically channels and routes to be the same as much as possible. So we are expecting the impact on DDR or on our experiment results to be minimum by spinning this platform.
Thank you, Emad. Will the heatsink differences, like the one that you were showing here, impact the performance results?
Yes, this is a possibility. Actually, generally these validation heat sinks has better cooling capability. One thing that we did, actually, we managed the RPM on the fan here on this heat sink to the minimum possible, just to get performance to be hopefully like pairwise with the original OEM heat sink.
Okay. Last questions. Let me make sure there's no other questions. So, on the slide 10 or 11, the graph that you have shown earlier, what do those various dots in the graph represent?
So actually, each one of these dots represent a reboot to the platform. So we rebooted the platform about 15 times in each experiment. And again, we let the kind of this platform, once rebooting, the parameters will be recalibrated, and we collect these margins toward the end of this recalibration process, basically. So multiple rebooting experiments here.
I see. And is there any plan to use the socket for the DDR5 and above?
Actually, I can explain this. I can't talk about this for now.
So there were multiple insertions completed during all this test that you show?
Actually, you mean like from cycling, like putting the package?
Yeah.
Yes, actually, no, we did not focus on that on this one here in specific, but we had done multiple cycling with elastomer and that SOGO bins in other experiments. So they are capable of multiple insertions, like hundreds of insertions for sure.
Okay. And how much is the total compliance in the SOGO and elastomer socket?
Yes, and the elastomer, it's about 0.15 to 2.2 millimeter, 0.15 to 0.2. In the SOGO, I think it's about 0.3 millimeter, the compliance.
Okay. I don't see any more questions coming in. I think that's pretty much, oh, one last question here. This is for the system level testing and manual, correct? This is not in the automation environment. I guess that's the question about.
That's right. That's right.
Okay. Alrighty, I think that's all the questions that we have. Thank you again, Emad, for presenting.
And lastly, I would like to thank our sponsors who made this event possible, including free registration. Our premier sponsor is Kohu. Our emeritus sponsor is JonsTech. Our honored sponsors are ISC, IWIN, and TSE. Our distinguished sponsors are Backer Hotwatt, Innovative Circuits Engineering, JMT, Nidec SVTCL, R&D Altanova, UI Green. Our exhibitor sponsors are ELELS, MJC, Phoenix Test Arrays, and Smiths Interconnect. So please, when you talk to them, thank them very much for making TestConX 2021 possible. And an extra special thank you to our premier sponsor, Kohu, the market leader in test interface solutions for the most challenging applications. And thank you to ISC, the global #1 total test solution provider. With that, I will thank you all for attending and wish you a very good rest of your day and look forward to seeing you again tomorrow at 7 a.m. Pacific time. So thank you.